Hi everyone. Hi everyone, good evening. You're all very welcome to tonight's lecture. Just a couple of formalities first to get through. Just in the event of a fire, we have exits here and at the top as well, on top left as well. Again, if you can all turn off your phones, please, that'd be appreciated. There will be opportunity at the end of the lecture for questions, so if you can hold your questions until then, that'd be great. I'll now hand you over to Joe Burns, who's a director with Arab, to introduce tonight's speaker.
Thanks, Dan. Ladies and gentlemen, it's my great honour to introduce Tristram Carfrae's gold medal address tonight entitled Designing with Computers, which was first presented a year ago, almost to the day, at the Institution of Structural Engineers headquarters in London. Tristram is Arab Group's deputy chairman and joined the company in 1981 after qualifying from Cambridge with a master's in mechanical sciences. In the early years, he worked with Peter Rice on projects such as the Lloyd's of London building. Tristram is responsible for the design of an impressive array of award-winning buildings throughout the world, such as the Beijing National Aquatic Centre for the 2008 Olympics and the Helix Bridge in Singapore, and is currently working on Gaudi's the Sagrada Familia Basilica in Barcelona, where the innovative use of pre-stressed stone panels as the primary structural element of the 6 towers reduces their weight and cost and dramatically reduces the time required to complete this unfinished symphony. Tristram has collaborated with some of the world's best architects, such as Renzo Piano, Norman Foster, Philip Cox, Richard Rogers, and Thomas Heatherwick. He has world renown for lightweight, long-span structures, and he has a reputation for challenging the established way of doing things, for exploring better solutions, and for designing better buildings that consume less resources, materials, energy, time, and money, and which yet give more pleasure. In 2014, Tristram was awarded the gold medal of the Institution of Structural Engineers. This is a very special award, and creativity is what sets gold medalists apart. Previous recipients include Fresnay, Nerve, Zienkiewicz, Calatrava, Ted Happold, and Arup himself. Tristram's citation from the institution reads as follows: "For excellence in innovation and design, contributing towards a better and more sustainable world, exemplified by leadership in an impressive array of iconic international award-winning projects." Ladies and gentlemen, I invite you please to welcome Tristram to deliver his address. Thank you.
Well, thank you very much, and thank you very much for inviting me here this evening. I'm afraid I had a cold at the weekend, so I'm a little bit croaky. I might have to resort to, unfortunately, only water to keep me going. So, designing with computers. What I'm going to do is illustrate this talk with some projects, which hopefully make the point that I'm trying to make in the talk itself. And between the projects, I'll talk a bit, if you see what I mean, and make the points I'm trying to make. But the first project then is from 15 years ago. So all the projects I'm showing you this evening are from the last 15 years, which is the second half of my career so far, and hopefully the middle third of my career when I get to eventually finish it. So this is the City of Manchester Stadium, which we designed for the Commonwealth Games, and now it's Etihad Stadium, the home of Manchester City Football Club. And the point here is that the roof structure, which is a cable net, is form found and to form a geometry which is totally independent of the roof itself. The roof itself is a perfect cylinder, but that's not the ideal structure. It didn't have enough curvature to work as a shell structure. So instead we put above that a form found cable net with pull downs in the corners, and then simply suspended the roof rafters from that structure. It's not a common thing to do, and I've never quite understood why it's not more common to separate the form of something from its structure. Normally we put the two together. We make roofs and walls, beams, columns, you know, and it's all one thing. But in this case, we totally separated them. Although, as you can see, they're not completely dissimilar. They're quite proximate, quite close to each other. Another point from this project was just a very small thing, and this relates to sometimes a small intervention can have a fairly major impact. In other words, there's no correlation in my experience between effort and outcome. Sometimes you toil very hard and get very little outcome. Sometimes one bright idea and you get quite a large outcome. So in this case, The roof structure is held up by these masts and pre-stressed cables, but there's a resultant force of compression running down the roof rafter that has to be resolved in some way. The easiest way to resolve it would be to use the raking beams that are already big enough because they're holding up the seats to turn up and just catch the back of the rafter. But if you did that, the roof would now be apparently supported by the seating bowl, and you would be a bit confused as to what all the masts and cables and stuff up in the air were doing. You know, it wouldn't be very legible, if you like. So a fellow called Alan Jones, who was visiting us from South Africa, Director of ARP in South Africa, came up one day with this really very elegant solution to this issue. He said, if we put a strut at the back of the rafter coming down onto the raking bowl, the rafter thinks that's the same as another tie up above it. So the rafter is now beautifully suspended from two ties from its midpoint, in effect, up in the air. And therefore it becomes a simply supported span with two cantilevers. And the rafter also then is minimized because the bending moments are beautifully distributed along its length. And we can go further and minimize it towards the outside end. So on the left here, you can see the raking strut, which we then use to support the cladding system. And you can see the rafter up in the air then tapers to the finest possible point at the end. And on the right, you can see we achieved the intent, which was to float the roof above the bowl. So visually, that strut is sort of vanishing behind the seating bowl, and it's being held up by the cables and the masts. And the other thing I learned in Manchester is that even though structurally it's most efficient to lean masts forward, probably by about 30 degrees, because that shortens their length, it looks far, far better if they lean backwards. Okay? Visually, it looks as though the masts are somehow balancing the weight of the roof, yeah? Even though the weight of this is trivial compared to the weight of that. But it just looks better. And the other thing is that when you approach the stadium, you live underneath the masts and cable structure up above you, all the way until you enter the door. If the masts lean forward, which I have done on previous jobs, as you approach the stadium, they gradually diminish until even before you've got to the door, they vanish completely behind the eaves of the building. Yeah? So it's sometimes you don't do what's structurally right. You do what's right for the project as a whole. And I think that's one of the things I learned probably too late in my life, really. It took me about 20 years to work out it wasn't all about structure. It's sometimes about the project. So about me, I'm shamelessly a practitioner. My job is to design structures and buildings and projects. Yeah? And that's what I do and what I love doing. I also spend half my time helping to lead ARP, a firm that I joined straight from university. I'd never dare try and go and get another job because I might get turned down. I'm much happier just staying where I am. But meanwhile, I've sort of fallen in love with the place. I love ARP's ethos of getting good people and letting them do what they want, of encouraging people to find their own way, their own methods of doing things. I'm not an academic, which is quite important given I'm going to talk later about how I think engineers should be educated. In other words, I'm talking from no knowledge, simply a view. And lastly, from the very beginning of joining ARP, I've used computers all my life. So I joined originally the Lightweight Structures unit in ARP, which was developing form finding software to develop fabric structures, the shapes of fabric structures using computers. Up to that date, we'd used physical models, soap films, stockings, all sorts of things, you know, twisted and shaped by a perimeter to find out what shape they should be. And we started doing it with computers. And in a way, I've never looked back, but I have that good fortune amongst my peer group to have never not used computers, if you like. So computers, what are they? They're not just big abacuses or fast abacuses. They've become far more than that. I was reading in the paper on the way here today that the average Briton, not the geeky Briton, the average Briton touches their smartphone once every 4 minutes and uses it for 2 hours every day of their life. Yeah, just think about that. And only 3% of that time is doing email, by the way, for the old farts in the room. That's not what it's for, okay? It's what we use it for, but it's not what everybody else uses it for. So you can see it's far more than just a calculator. It's how we communicate, obviously. It's where we get our information. You know, if you want to know something now, you look it up on the web. You know, I've got a set of Encyclopedia Britannica at home, but I don't think it's been opened for 15 or 20 years. It's how we manage processes. All project management is now done by computer software. And it will become where we visualize and analyze data much more so than today. So the whole big data movement is coming. It's with us. Now this is a very potentially pejorative slide, so please don't take it literally. This is just a sort of a snapshot of attributes that you might assign to people like me, the baby boomers, and the younger generation, the millennials. Now, I apologize if anybody in the room is a Gen X because they're missing. It's not because I don't think they're important, it's just I want to make a point about the two ends of the spectrum, the people leading the practice and the people doing the work who've just arrived. The one I want to pick up in particular is halfway down the millennials. There are two attributes that KPMG found from a survey of about 5,000 graduates around the world, that millennials want to have strong mentors and coaches, and they want to collaborate with inspiring colleagues. So I just want you to bear that in mind as we go through the rest of the talk. So even more pejoratively, I'm saying that this is how boomers go about structural engineering. They think from first principles. They try and work it out on a napkin after a good meal in a restaurant and draw it. And then they might get somebody to analyze it to make sure it works. Yeah? But I think they've sorted it out first before they resort to the technology. And it's a sort of linear process. I'll think about it, I'll draw it, I'll analyze it, it's done. Yeah? We'll pass it out the door. Millennials who've used computers all their lives might have a slightly different approach. They might be prepared to dive in and give it a go, yeah? To try it using technology, to learn through the use rather than learn from their experience or solely from their experience. The two other things I've added there, which came from David Nethercott, an ex-president of the iStructD, but also a professor at Imperial College. And he said he's noticed that we work in ever smaller teams because we're more efficient and effective as a profession than we used to be. Our fees are half what they used to be. And a consequence of that is that the younger generation have fewer people to turn to ask questions, fewer people to learn from. And if they're the only people using the technology in the team, they're under incredible pressure to deliver. Yeah, and it's sort of not right. It's not fair, if you will. So back to projects. This one's 12 years ago, 2003. Actually, it's 13 now. It's a year since I gave this talk. So this is the Beijing National Swimming Centre, the water cube. And here I borrowed an idea from Dennis Ware, who's a professor at Trinity College Dublin, and I borrowed it totally shamelessly without his knowledge, because luckily he published it on this font of all information, the web, and I found it using Google. And so I took his geometry for a perfect array of soap bubbles and made a structure out of it. So I was inspired by the photograph you see on the left, which I thought was some organic material. I thought it might be a bone structure or something similar out of biology. It turns out to be a foam, believe it or not, a polyurethane foam. So it's not surprising that its geometry is very similar to this perfect array of soap bubbles, which is a foam. Okay? So anyway, we carved the building out of this array of bubbles using a 3D CAD software. So we ended up with a structure you can see in the bottom right by the time we'd done all the chopping and cutting and shedding the sides. And so you end up with a structural analysis model like this. Now, I didn't look at this model seriously until we won the job. And so you go from this really euphoric, we've won, and you've been fighting every step of the way to win and persuading people that you know what you're doing and what they're looking at isn't idiotic. And then you wake up one morning and look at this and say, I wonder if it works. It looks like a structure. I thought it sort of smelt like a structure. It felt like a structure, but was it one? And in particular, was it an efficient structure? More importantly, so this is a structure with 24,000 different elements joining together at 12,000 nodes, and every single connection is a moment connection. It is not triangulated in any shape or form. And what I found is I couldn't make it into a structure. I couldn't assign sizes of elements to this in a way that made any particular sense. Either they were too big and the whole thing was too heavy and it fell down, or they were too small and it was too weak and it fell down. And I couldn't find any balance between those positions. But I was still convinced it felt right and it looked right. It was just complex. So after a month of trying different things, we came up with a process, a mechanized process, to decide to find sets of members at work. So all we did in the end sounds very simple now, but we tried lots of other strategies, was to start with everything really, really small, analyze the structure under all of 200 odd load cases, compare the results to the Chinese steel code in every particular: shear, torsion, bending moment, axial force, including effective length. And if the member was too weak, just make it one size bigger. And if it was too strong, make it one size smaller. So the trick, it turned out, was not to try and jump to a solution, but move to a solution by increments. And what we found is that after 25 iterations, it converged on a solution that worked. And by the way, I now know there's no mathematical reason why it should converge, and in fact a lot of structures don't. But this one, fortunately, it did. And it weighed the right amount of steel. We're in the ballpark. We've got a roof that weighs about 60 kilos a square metre, spans 120 metres. That's good enough for me. And this was the outcome. So here you can see the big purple members are the fat ones, and the tiny little skinny red ones are the thin ones, and all the others are in between. And you might get an idea why I couldn't guess which one went where. Yeah? And in fact, if you run the process again, you get a completely different answer. There are probably more than 1 million different solutions to this puzzle, because it is so the opposite of determinate. It's such an indeterminate structure that there are tons and tons of solutions. But all we needed was one elastic solution that we could give to the Chinese authorities to prove it complied with the Chinese steel code. But then we went one step further. We realized we created a set of geometry inside a machine. We'd worked out what sizes all the elements should be inside a machine. If we could work out how to connect them together inside the machine, then we finished the job. We have the structure fully defined. And so we invented some rules as to how to size the nodes. We chose a simple idea of spherical nodes because it's something the Chinese understood. They used it quite commonly anyway. It also means that all the tubes can just be square cut and they'll always meet the sphere properly. And it just needs a simple weld to put it together. Anyway, we then realized we had 12,000 nodes to design, and it's not easy to design a sphere with 4 bending moments and shears and axial loads coming into it from different sized elements for 200 different load cases. So we took a statistical approach. This was perhaps me going out furthest on a limb than I'd ever been before, because we decided that if we sized all the nodes using a rule, and then we tested 10 of them accurately, as in meshed them up as a finite element model locally, and they all worked, then the other 11,990 would also work. It was unlikely that they wouldn't. And it's not so silly. It's like the way we test a bit of existing concrete. You know, we go in and take 10 samples and we look at it and say if they work, then probably, you know, the strength is about right. It's not completely mad. What was, I thought, completely mad is the Chinese authorities agreed with me. And that's what we did. Now, once you've got the whole thing in 3D, you can do all sorts of other things. Just, you've got to remember that this is 2003. This wasn't last year. So for me, this is sort of like opening my eyes to possibilities, because you can start producing what you see in front of you in visualization. Now, in those days, visualizations were done in Photoshop by sort of artist-stroke architects. They didn't start from a 3D model. But here, what you're looking at is a render of the actual structure itself. We've added the ETFE for show, if you like. But every single member you're looking at there is the right member with the right wall thickness in the right place, connected to the right node. You can make physical models from your digital model, so you can see what it looks like if you wish to. That was actually a hard ask. Nobody had made a rapid prototyping model with 24,000 different bits before then, but we did get it done. And then you can deliver this information to your contractor in any way you want, because it's one set of data. It's one model. So we could deliver it, as you see on the left here, as a sort of illustrative diagram with numbers and then a whole spreadsheet or database, in fact, of all the information that went with it. Or you could deliver it as in the top right, a conventional set of 2D drawings, or in the bottom right, 3D illustrative drawings. It didn't matter how you delivered it, because it was all different views of the same data set. So up until then, I'd always delivered documents as 2D drawings, and if the contractor wanted the 3D information that sat behind it, I'd give it to them in a pub in a brown paper envelope and say you can't rely upon it. Okay? Because otherwise you have potential conflict between which is the contractual information. Is it the 3D model or is it the 2D drawings? But in this case, because nobody touched anything with their hands, it had all been done by a computer process from beginning to end, I could trust all these different representations as being of the same thing. And to me, that, that's where we're going. That's what BIM models are all about. It's all about being able to properly articulate what you want with an accuracy you can rely upon, and then leave a contractor to deliver it through manufacturing, through construction, through whatever processes in a way they want to. And I'm going out a bit further than probably reality. I can see some looks of skepticism around the room, but bear with me. It's a direction rather than an absolute. And then the strange thing is that the Chinese decided to build it by making all the bits and then bringing them to site and building the world's biggest scaffold and welding them together on site in situ. And I still have no idea whether the right bits were in the right places. Okay, I'm pretty sure there were none left over, so it must be approximately right. And I can be so blasé because actually it's such a redundant structure, it probably doesn't matter. In fact, you could probably remove half the members there and you've still got a structure that works. It was just very hard to prove it elastically. And in fact, they did a piece of wall at 1/3 scale and pushed it over as a static pushover test to test the seismic resistance, even though we convinced them that theoretically it should be correct. It took a 100% of gravity laterally and was still standing up reasonably happily. So I will claim that this is the world's most seismically resistant structure. What benefit that is to anybody, I don't know, but I'll claim it. And what we created was a space that was different to usual. The purpose of all of this wasn't the structure, it was to make the building light, to allow natural light and the sun's energy to heat the swimming pools. In the main competition pool hall, we couldn't let in more than about 5% daylight because the television cameras would then have said, we have to black it out and we have to use artificial light to get good Olympic television. But at 5% daylight, we could persuade them to leave it naturally lit, augmented with artificial light where necessary. And this is Mike Phelps winning his 7th gold medal. But alongside that, there were 45 world records were broken in this pool in the 2008 Olympics. And I still believe it's because it was such a beautiful place to swim, and it's nothing to do with the Australian shark skin suits. Okay. While we're in Beijing, this is, I think, probably the world's most beautiful stadium. But it's not the world's most efficient structure. Up the top there, above the red bit, is the roof. And it's 13 or 14 meters of roof trusses are spanning 300 meters across this stadium, holding up the pattern that you see in front of you. About 25% of the pattern you see in front of you is structural, and about 75% is decoration or camouflage or art, if you like. So I set out with my favourite Australian architect, Philip Cox, with an ambition to say, could we, together, come up with a form that Philip thought was beautiful and I thought was structurally efficient? Could we, instead of making the structure a servant of the art or the architecture, can you do both at once? And the result was this stadium we built in Melbourne. It's a small stadium, it's only 25,000 seats. But we did it with, having decided the overall form, we then used parametric modelling. So on the left here, we're adjusting the red line and all the rest of the lines follow. And then having got a parametric model of whatever with a certain type of adjustment, we then look at, does it look nice? Is it good architecturally? Is it aesthetically a nice solution? It's then we sized all the elements with the same technique we developed for the water cube and could say, is it lighter or is it heavier? Is it more efficient or less efficient than the one we had before? We looked at the panelization of the facade. How much repetition are we getting in the triangles on the surface? Is it a more efficient facade or a less efficient facade from that point of view? And we could look at it in some detail. This is a CGI from about 9 years ago, and it's pretty close to what we actually built. So we're beginning to also get this visual representation from our simulation. So I'm beginning to say it's not analysis anymore, it's simulation, and simulation of different facets of reality. It's only an approximation, but it's getting closer. And we built it, and I'm glad to say the roof is not 13 metres thick, it's 273 millimetres thick, and no longer needs a soffit cladding. It just needs a roof cladding because the structure is on display, it's part of it. And I quite like these little pockets you get under the roof. So people get to own a bit of the stadium. That's where they go and watch from. Other people go and watch from a different bay, if you like. So it's not just a continuous grandstand, it's got a bit of subdivision, a bit of granularity. And ultimately, it just looks pretty special. So this is it sitting in Olympic Park in Melbourne with the city behind it and the river in front of it. And that's not a CGI. That's reality. That's what we built. Another project with Philip Cox, we went a bit further. This is a high-rise 40-storey tower, commercial tower in Brisbane. It's on the waterfront and it sits between two buildings, you can see there left and right, designed by Harry Seidler, who's Australia's probably best modernist architect. It shouldn't be there, our building. Nobody should have given permission for another building to be inserted there, but they did, right? And therefore we had to deal with that site. And on plan, the big grey blocks here are the two existing buildings, and our site is in the middle, and it's sat right on top of an existing podium and basement. So that the podium and basement was already complete for the two buildings that are already there. And in particular, the goods loading dock ramp went right through the middle of our building. So we faced a choice. Do we rebuild the basement and the podium to suit what we want? Or do we accept what was already there and adapt our building to suit that? And we chose the latter. And it had some pretty sort of profound consequences. The first is that the core is a long way off centre to avoid that ramp. And in the cyclonic winds of Brisbane, it was no longer able to resist the wind load alone. So we had to have a perimeter wind frame to supplement the core. And the other thing is the perimeter columns, we chose places where they could be inserted through the basement with minimum obstruction and disruption to the existing basement. So they came up in a sort of random set of locations. And it was that randomness that then led us to generate a random structure sitting on top. Because if it started random, why not just continue? Why not make a virtue out of necessity? And we did this by writing about 3 pages of Visual Basic to generate a structure that would work. But we didn't try and predict what would work and then construct it. We let the computer continually generate options until one passed the test. So for every floor, you knew where the columns were already from the floor below, and the computer generated a random set of columns at random inclinations, and then tested them against some basic structural sort of principles. For example, do we have as many leaning left as right? Do we have as many corkscrewing clockwise as anti-clockwise? What span is the edge, maximum span of the edge beam of the floor above? And do we have an average inclination of about 10 degrees, which is what we need to resist the wind load? And all it did is it just carried on generating random combinations until it got one that was lucky, that hit the mark. And then it put that in the computer and moved on to the next level and did it again and again and again. And after about 1 million iterations, it would get to the top of the building. And we'd say, well, actually, we don't like that very much. Let's change the program a bit and do it again. And then after a while, we said, we do quite like that. And so we'd make 20 of them and take them down to see the architect and say, what do you think? And he would say, I don't like it either. So let's take, so we go back and turn the program and do it again. But anyway, a week later, after we'd begun, we had this. We had one that we were all happy with, one that worked structurally, that he was happy with visually. You can see that the columns get a bit more excited towards the top. They start becoming a little bit more wavy around because that we thought looked more natural, but also you can because they're not carrying as much load up there. Down the bottom, they're quite disciplined. They're quite thoughtful in the way they go about their business. And it does actually work. On the left here is a model showing the vertical loads shared reasonably evenly between the columns. There's less at the back because the core comes to the perimeter at the back. And so it starts taking the load, sucking the load out of the gravity system. And on the right is the loads under wind load. And you can see you're getting the compression in the downwind face the way you should. So it does actually work. And the reason I say that is a lot of people, including structural engineers, have told me that can't possibly work as a wind frame. Because it hasn't got any triangulation. But it sort of has, and it's sort of got a moment at every floor. And it's got enough to make it work, and it does. And this was another breakthrough for me, another eye-opener. On the right is the engineer's Revit model from 7 years ago. On the left is the architect's Revit model. And they're the same thing. They've actually got the same geometry. You know, we spend our life normally altering our drawings to match what's happened to the architecture recently, and we're never quite sure when we deliver our set whether they're coordinated or not. In this case, they had to be, because there was only one model, the one that we generated initially from the computer, that was then shared between us. And we built it. And delightfully, if you like, the story is that at the front of the building is this fig tree on the left that sits in the middle of the road outside the front door of this building. And we have grown our columns just like vegetation using the principles of phototropism. And afterwards, when we get to Q&A, you can ask me A, whether I know what that means, and B, whether it's true. So the middle bit of the talk is a sort of intermission. I'm going to talk a little bit about design. So this is off topic, but to me it's equally important. And this is about having an attitude about designing something. And I think it is just an attitude that you strive to do something that's better than whatever is the norm. Now, you can define better any way you want, you can define the norm any way you want, but it just means being critical of the usual answer and saying, is there a better solution? And of course, there may not be one. You know, you may just do what's normal because that might be the best solution available. But it's the attitude of taking that on at the beginning. And it makes you into quite a nasty person to live with, as my wife at the back will probably vouch for, because everywhere I go, I question what's going on. And particularly if she tells me a piece of news when I get home in the evening, I'll ask, where do you get that from? You know, are you sure? Because you become this sort of critical person. You know, why is the door handle where the door handle is in my hotel room? Surely it'd be better if it was an inch higher, you know, or it should be a lever rather than a knob, or whatever. You know? And then the second bit is you're looking for an outcome. So the best thing here I can do is to tell you a story from Peter Rice, Irish engineer who I once had the great pleasure of working with. And Peter once looked over my shoulder and he sort of shook his head a bit and he said, look, Tristram, you're trying too hard. It doesn't matter how clever your structure is. Nobody cares. The only thing they're going to care about is how they experience it after it's built. So it's all about the outcome. It's all about the people who are going to inhabit the built environment and their experience. To some extent, but maybe a bit less, it's about the people who run their business using the built environment, like retailers, like building owners. But it's really about the community. It's about people who either occupy or pass by or use whatever it is that you've designed. And the last one is the struggle we have as engineers sometimes, is this open versus closed. I think we are taught too much mathematics. Okay? So hear me, not an academic, pronouncing on what we get taught. The reason I think it's a concern is that the way we're taught mathematics is we're taught to solve increasingly difficult problems that only have one answer. And so we get very adept at classical problem solving. But the real world and design are the opposite of that. There isn't one answer to a design problem. There's an infinite number of opportunities. And it's not about finding the best single solution. It's about looking at all the possibilities and using your instincts as much as your logic to decide which ones you think might be better. Because the parameters you're comparing them against are so complex and so numerous, it can't be reduced to a single mathematical equation. It's not 2 + 2 = 4. It's what can I possibly do? And to illustrate that most, I'll say that most engineers are rather frightened by a blank sheet of paper. But when you have a blank sheet of paper, it's the time of maximum opportunity. It's when the greatest outcomes are available to you. Immediately things get fixed, you diminish the possibilities. But unfortunately, that's where engineers get more and more excited. And when you work with an architect like Zaha Hadid, for example, where your challenge is to make something slightly ridiculous stand up, you know, you think that's the best thing that could possibly happen to you, because you've got this thing that almost doesn't work. And so you're in that mathematical issue of solving a really complex problem. But you should ask yourself, really, is that the right starting point? Should we start with a proposition? And please don't, I'm using Zaha as an example here, just to make the point more real. It's not, I have a great appreciation of Zaha's architecture and have worked with her a lot, so it's nothing to do with that. It's just this idea about when do we come to the party, and do we normally come in too late after things are fairly well defined. So for me, there's an approach to design. It's about thinking about outcomes first. It's challenging the status quo, and to do that, by the way, you have to know what the status quo is. So you have to research. You have to find out what have other people done with similar projects. You know, what is the norm, or what is the best of what's done so far. Yeah. For me, I always try and look at efficiency and delight. I call them. They're the costs and the benefits. Sustainability for me has never been very satisfactory because it always addresses costs, and it very rarely talks about benefits. And in the end, we're trying to make a better built environment, a more delightful one, one that functions better, one that creates healthier places, safer places, whole set of criteria. So value for me is maximizing that lot and minimizing the costs in terms of materials, time, money, you know, all the things that you can measure. And then ultimately for us, of course, you've got to deliver it. It's not just some intellectual game that we play. Things get built, they have to work. And we have to be relied upon. We are relied upon by society at large to do that. So it's a process, design. Conceiving ideas, simulating them, I'm going to say here, perhaps in a machine or perhaps with a sketch or in any way that suits you most, testing them, then judging whether you think you've got a good solution or not, or whether you're going in the right direction or not. And it's very important, that word judgment. It's just as much about intuition and hunch as it is about logic and precision. Yeah. And then you iterate, you try again. I found that I can only do about 2 hours a day on any one design problem before I'm getting stale. I then find I need to think about it overnight. Use your subconscious, relax. And it sort of happens in the back of your brain is where you do this judgment, where you reflect on what you've learned from the day before and you strategize what you're going to do in the next 2 hour stint, if you like. Like maybe when I was younger, or maybe younger people can do it for 8 hours or 10 hours or 12 hours, but I can't. So the technique is to get your brief right, understand what you've been asked to do. What's special about this project? So if you're given a hospital to design, don't think, well, I did a hospital 5 years ago, I know what this is, I'll get on with it. You've actually got to cross-examine what you've been asked to do and find out what's special about this hospital. What's its situation? What are we trying to achieve? Is it going to be naturally ventilated, for example, to get better patient recovery or not? Now, what are the aspects of this hospital that are important? You've got to get stuck into it a bit, because otherwise you won't understand what it is you've been asked to do. So you've got to start thinking about solutions. Then you go and investigate what the best solution available to date is, as I said before, the research phase. Then you set your ambitions. What will good look like on this project? What will the press release read when we've finished that will make us happy? Okay? What are we trying to do? And then you get stuck into it, as I said before, with the process I've just illustrated on the slide before. So the point about this is that the design process is slightly uncomfortable, I think. It's not something where you know the answer before you begin. It's an exploratory process. It's meandering. It's very unpredictable and even slightly messy. And partway through it, you're vulnerable. People can ask you what you're doing, and you don't really know. You just know that you're sort of feeling your way through a whole lot of different possibilities. So it can't be planned. That's quite terrifying, isn't it, really? You're setting out on a process where you can't really have a decent plan. You know, probably you've got a time frame at which you have to stop. Yeah? But that's about all. And in our app, we've sort of asked ourselves the question, can it be taught? So we're running courses now for our senior people about conceptual design. Because I met somebody who said it wasn't just an innate skill that you either had or you didn't have. It's actually everybody can be taught to design. So we're trying that, and hopefully it'll be successful. So a couple more projects. This is the Singapore Sports Hub. This is now 5 years ago. An important thing here, this is a design and construct project, and not one in the same context you might know design and construct in Ireland or in the UK. This is design and construct whether you and the builder start from a brief from the government, which is, I want a national stadium and I want this capacity. Yeah. Then you compete against others and then the government will choose as one team, and you've got a fixed price by that stage, and you get on with it. But you fixed your price against a very outline design, but a set of performance criteria against which you have to perform. So this is a 300-meter diameter dome. In fact, it's the world's largest dome. It's a big thing. So here it is in cross section, and here it is with the Sydney Opera House inside it, just to give you some idea what, you know, what's 300 meters. Yeah. And the roof has got this moving component at the top, so and it's creating lots of different environments. So we've got a transparent piece at the top, which means we have to have a really solid piece to keep the Singapore heat out for the rest of the roof. And then we have a naturally ventilated brise soleil around the perimeter as part of a public concourse system. 3 different parts of it. And this is what they look like when we finish. So the top bit is the transparent bit, the fixed bit, and the louvered bit. The trick to making this roof weigh only 100 kilos a square meter, which was the outcome, is for it not to weigh 300 kilos a square meter. Now, I know that sounds a little bit of an obvious statement, but if it weighed 300 kilograms a square meter, it would have to hold itself up. When you get to a 300-meter span, you get into this sort of point of no return, where you just add steel to hold up steel to add steel to hold up steel. And the trick here was to keep the moving roof as light as possible, because it's a moving load. So on the left, you see the deflected shape when the roof is shut, and on the right, you see the deflected shape when the roof is open. Yeah. So if that weighs a reasonable amount, then obviously the fixed roof has to weigh an awful lot to hold it up. Yeah. So it's the top of the pile of cards, sort of thing. But everything we've been told today about moving roofs is to make them work, they have to be on stiff rails. And they have to be stiff themselves to make sure that the mechanism won't jam up, so you can predict what it's going to do. So we had to chuck the rule book out and start again, because if we're going to have a roof that overall is efficient, the moving roof has to be light, and the fixed roof has to be flexible. We can't have additional stiffness. So we redesigned the moving panels from scratch to make sure they had only 2 points of support and then a hinge between them, top left. So they'll always sit on their rails, whatever happens. We changed the mechanism, and it took 6 months to do this, to the simplest possible mechanism. So rather than having winches in winch rooms down below and cables coming all the way up the roof and round pulleys and back down and holding up the moving panels, the winch actually is mounted on the moving panel itself. It's sort of the last place you'd first think of putting it, but immediately you have put it there. It's so obvious, because all it now does is lay out the cable as the roof goes down and winds the cable back in again as the roof goes up. The cable itself never moves. So there are no pulleys and there are no reactions. When you take cables around pulleys, you get a reaction that's twice the force that you've got in the cable, all of which then has to be supported by the fixed roof. So it's going at everything from first principles. How can we do a flexible roof? Because we don't want to do a stiff roof. The wind loads we examined in great detail. So we got the actual real-time pressure distributions out of the wind tunnel and then analysed them for the worst effects on our roof. So we ended up with 200 different patterns of loads. Each one would have a different effect on different parts of the roof. But by doing so, we reduced the applied wind load by 40% from putting a blanket load on it in terms of its effect on the steelwork. Each steel piece, again, is designed for its location using the same technique from the water cube. But in this case, we said, well, actually, we want the top chord members of a truss to be the same diameter, which is a bit silly moving the cord, you know, up and down all the time in diameter. So you just choose the wall thickness. So all the members at the top of the screen on the right are 508s, the middle section are 457s, the bottom ones are 356s. Yeah, we're just changing the wall thickness to optimize them and make them the right size. But the cleverest bit was something different. This shows the overall truss arrangement for the roof, and the big bracing trusses. You might think, you wonder why they're there, the big triangulating ones, and it's because it's held together at its base by a big concrete ring beam, a post-tension ring beam. And to make the ring beam work, you have to thrust radially at it. It doesn't like being pushed out in the middle. It'll just come in at the ends. It'll just oval. Yeah? And so what the bracing does is to make sure that the forces in the roof redistribute themselves to keep that circular thrust on the bottom. But the other point is that these, up in the top, the beams that cross over the hole in the middle have to be 5 meters wide and 5 meters deep for stability, 5 meters deep to take the bending moment efficiently, and 5 meters wide to stop them buckling in compression as the whole shell works. But down at the bottom, they didn't have to be that big because they're not working as hard and they've got secondary trusses stabilizing them. So down at the bottom, we made them only 2.5 meters by 2.5 meters. So we persuaded our design and construct contractor, who's already delivered a lump sum to his client, that it was in his interest to continuously taper these trusses from 5 meters deep to 2.5 meters deep, so that people had a better experience when they were in these concourses. So it would be a better building. The consequences, you know, were not just to the steelwork, but you can see in the top left here, we had to do all the reinforcement detailing in 3 dimensions to get the reinforcement into the buttresses, because we probably had gone a little bit too far, and maybe 3 meters by 3 meters would have been a better solution. But anyway, the point is that 2.5 meters is a sort of human scale thing. So people can understand it and they can relate to it in real life. At 5 meters, it would have been a different thing altogether. So again, you know, persuading a design team, including a contractor's team who's got a lump sum on the table, that those things are important, is a good outcome. Here I like this picture because the final product is, if you imagine the roof closing, there's a piece below the moving roof that always stays open. And that's so that people in the stadium can always see the city of Singapore, and people in the city of Singapore can always see into the stadium, because most stadiums are hermetically sealed. You know, you've either got the ticket and you're at the match, or you're not. You know, and here you get this idea that actually the city and the stadium can always have a relationship, even on match day. Okay, so this one's about about building in the desert. Okay, what is it about the desert in the Middle East? And I'm saying it's hot and it's dusty. And the normal response to that context is to use monumental masonry. That's how the souks and things are kept cool, is you build with a lot of mass. And so for this airport in Kuwait, with Foster and Partners, that's what we set out to do. But again, it's not a trivial airport. You know, that airport put in the harbour at Hong Kong would make the staff very redundant. It's 1.2 kilometres from tip to tip in a triangular shape. And what the architect wanted was to make the roof out of concrete. The largest concrete roof that we've been involved with so far was Duxford Airfield, also with Foster's, and it's about 100 metres. This is 1.2 kilometres. Okay. And for me, it didn't feel very comfortable to do a roof of that scale in concrete. And the geometry was already decided and included this wonderful feature on the edges of the roof to shade the glazing and to give this grand porte cochere. We had a 60-metre cantilever in concrete. I found out from Jack Zuntz, the ex-chairman of Arup, that when we did our first concrete vertical high-rise building in South Africa, it was 60 metres tall, and we were worried about whether that could be built in concrete. Prior to that date, we'd always used steel. But here we are going 60 metres horizontally. So we split the problem into 2 parts. At the bottom, we're using concrete beams and post-tension tie cables up in the air to make massive cantilevers, outwards and inwards, balanced cantilevers, if you like, all the way around the perimeter of the building, which left only a tiny bit in the middle that wasn't made that way. And on top, we have these shell structures, and they're totally non-repetitive because we've also got this beautiful arc on the building from low at one end, up in the middle, down at the other end. And the consequence of that is that every single shell is different in its geometry. So we came up with this idea of fruit box engineering. We take steel plates that are laser cut and accurate, and we make them the formwork, the permanent formwork, into which we will cast a piece of concrete, which will be the skin. And then they're bolted together using the steel cruciforms you can see in the bottom right, which are also accurately made, either cut from very thick plate or cast in a way that we can make them correct. And if it all then gets bolted together correctly, we've got the shell we first wanted. There's no tolerance in any of this other than the 2mm oversized holes. Apart from that, it has to work. But the problem is the concrete shell is good in compression, but it's not very good in tension. And we're dealing with temperature ranges here in the desert, which are quite large. And so we've got the problem that when it heats up, it's okay, it goes into compression, but when it cools down, this whole roof will open up, and if it was made of monolithic concrete, it would crack. And how do we stop that and still have a roof that works in compression? How do we balance those two things? And one way is to put a lot of movement joints in the roof, but I hate movement joints. I think they almost always go wrong. And so we decided to do this roof with absolutely no major movement joints over its 1.2 kilometre length, and instead design these pieces of concrete to flex slightly. So the cruciform is offset from the concrete, so that all the joints can open up by about 0.5 millimetre each, and then the whole roof can flex and breathe without losing our shell stability, because all the steelwork is still being held together. Now it's an easy thing to say, it's not an easy thing to prove. It's very hard because you've got to hit this middle where you've got the right amount of flexibility to relieve the thermal issues and sufficient stiffness to keep it all stable. And you've got to be in that zone. So we modelled everything with incredible accuracy. This is a dyna model, a non-linear model, where every bit of steel, every weld, every piece of concrete is modelled to try and work out the behaviour of a panel. Then a panel assembly, as you see in front of you, and then an assembly of a whole piece of the roof. Our PCs aren't capable yet of doing that across the whole roof, so we just do one bay. The other bays are approximations. To get this feeling for does it work? You know, can we investigate this sufficiently in a computer to be confident? And I don't know the answer to that yet because we haven't built it. Okay? And I'm not quite sure if I want it to be built. Maybe I do, maybe I don't. But if it does get built, this is in Kuwait, by the way, then this is what it'll look like. This idea of caves. You know, and you can see the idea that the way it might be a hospitable place in a hot climate. This idea of cool caves for you to go and sit in. So last bit of talking, back to computers. Okay, I've said this already, they're pervasive. Right? We use them for everything. We use them for analysis and modelling. They're where we get knowledge. We use them to collaborate. Increasingly, we use video conferencing and link and screen sharing and all these things to collaborate with other people. And ultimately, I put to you, we will deliver data sets of our projects, not drawings and specifications. The analog age is dead. It's finished. It's not the future. So how should we do structural design? I'm suggesting we should do it by simulating as best we can structural behaviour, by experimenting, by learning and exploring, by prodding and poking. Now this is totally different from what I hear my colleagues say, well, the kids just build a big computer model and assume it's right, and it's not. I'm not saying that at all. I'm not advocating that. I'm advocating building tons of models at lots of different scales. Simple models, complicated models, models of details. You've got to, if you're going to rely on the computer, then you've got to use it in anger from every single possible direction to cross-check itself. Okay? And it's a meandering and non-linear process, in my view. Don't think you're going to just go from A to B and come out the other end. This is another aspect of computers. It's going to take away a lot of what we do today. Will be done by the machine. Everything that can be automated will be. Well, I particularly like the bottom quote from one of our directors. Everything inconvenient will change. So everything you don't like doing or is a bit boring, you're not going to be doing in the future. I've said a bit of this already. You know, it's so important that we teach our younger engineers to check what they do. It's something that's sort of died out of our industry. When I started, everything was checked. Initials were all over everything. Somebody had checked your work. Yeah. Now we sort of don't. It's a sort of self-check, but it's not formalized. So we've got to inculcate this idea that everything has to be checked somehow. Cross-checked using a different computer model, done by somebody else. I advise people after the concept design stage to chuck your models away. For scheme design, start again. Do it again at the end of scheme design. Because that is in effect a primary check on what you did before. Can you recreate it from scratch? Yeah. Same with calc plans. The number of times I've come across projects with problems, and it's because the wind load was wrong because somebody put it in a calc plan on day one and nobody else looked at it. They just assumed it thereafter. So again, I say don't chuck it away because you need it, but put it to one side and write a new calc plan, and then look back at the one before and make sure, you know, correlate them. Have you got the same answer the second time? Disposable models. Do tons of models. Throw them away. Use them just to check things, but don't keep them necessarily. Sensitivity studies, as I was saying earlier. It's not a bullseye game. This is a game to make sure you're in the vicinity of things that work, that your bands, upper and lower, will work. You've got to often use different yield stresses, and if you're really pushing steel, you've got to actually look at what the real yield stress is likely to be, not just the one in the book, because actually it's much higher than that, and sometimes that's important. And in the end, it's sufficient accuracy. We choose loads with about a plus or minus 25% accuracy at best. And then we assume we design steelwork with 2% accuracy. It's just fallacious. It's not how it works. Yeah? Everything is somewhere around 20%. That's the mindset you should have in what you're doing. So the other thing is not to believe that the computer is true. It isn't. It's just a view. Yeah. So what do we teach people, or should teach people? You've obviously got to teach physics. What makes things stand up? How do they work? Stability, plasticity, materiality. All these things have to be taught. I think we should teach how computers work, in theory at least. What is the basics of matrix arithmetic? What are the basics of dynamic relaxation or other nonlinear techniques? But I also think we should teach students to explore structural behavior. But I don't think we do that very often. We again tend to give them problems to solve where there's one answer. Tell me the bending moment on this. Yeah? Not exploring structural behavior. Locating structural opportunities. It's the inverse of exploring structural behavior, if you like. How could this structure be made better? What would you do if you started from here? Where would you go? Yeah? And you might learn more if you use physics engine. So this is about instant gratification, if you will. If you use the physics engine in which some games, computer games use, you can build things and get instant, it either stands up or it falls down. And you might learn more from that than taking your time to build an accurate computer model and 2 days later getting a set of stresses. Because in your physics engine, you can continually test and try and test and try and learn on the spot. I'm not saying I know that's the right thing to do. I'm just saying you should think about it. And lastly, of course, we don't design in isolation. We're only the structural engineers. So it's about integrating your skills and experience with others and caring for the whole project, not just your part of it. So here you go. This is my proposal. And my proposal is aimed at my generation, the baby boomers. It is absolutely important that we get our heads around technology and what it can do. I'm not meaning that we have to be adept at actually using the software. I don't think we have to be able to build the models. But we do have to be able to sit with our design teams and interrogate those models and understand them. And to say you shouldn't be doing it, you should just be drawing sketches and using your head, is not the right answer. We will use technology more and more. We will design in a virtual world. We will simulate our structures. And to tell the younger members of our teams not to do it that way is not the right answer at all. Okay? So it's a big obligation on us because we have the knowledge and the experience that are needed to make sure we don't make mistakes, at the very least, if not needed to make better structures. So we've got to engage, because I see some of my generation as project directors gradually stepping away from the technical part of structural engineering and assuming that the people using the computers are getting it right. Okay. And I don't think that's good enough for our industry. So last project, and because you've heard the introduction, you might be able to guess what this is. Okay? This was the original design of Sagrada Familia. So this was a church that was under construction in 1880, and the crypt was already built before Gaudi was appointed, and he redesigned it to be this on the right. So on the right, the red line is what was originally designed, and the grey blob is Gaudi's church. And it brings us to a particular problem, that the tower in red here, the Mary Tower, and by the way, the 6 big towers in the middle here aren't constructed yet. If you've been to see the church, it's only the 4 towers in the front of this view and on the back. The 4 towers on the right aren't constructed either. But anyway, the tower I'm going to concentrate here is the Mary Tower. And the issue about the Mary Tower is it sits on the crypt. So it sits on foundations that had no idea that a tower of this scale was coming later. So the problem that the design team, the Spanish design team had is, how do we design this tower light enough to sit on foundations that were put in 1880? And that's the construction to date. So it's the base of it is already present. It's up to this lantern, and the question is, how do we design the rest of it? And it's got a complex geometry, which is a typical Gaudi ruled surface. It's all made up of a set of intersecting hyperboloids. So it's a tower that has its own sort of tapering shape, but it's made up of these concave surfaces. And so when we first had a look at it, I have to confess I have no idea in my head how a structure like that works. How do those two different surfaces interact? How does it work as a tower? And can we make it out of stone? Was the first question I asked myself. So I went straight at it. I built a computer model. Now I think my laptop will show that over 2 weeks I built 57 different computer models of this one item of Sagrada to try and find out how it might work. So this model, all the elements in front of you take compression only, except for the hoop elements, which have tension capability. And this shows what happens with the structure when it's under a service wind load. And it's more or less working. There are enough compression diagonals, to keep this going. There's a little bit of lack of stress in the windward face, and a little bit too much stress maybe back at the leeward face. But when we put the ultimate wind load on it, it looked like this. And while that's still standing up, it's not a structure I was very comfortable with. Most of the structure is now slack or cracked or open with joints open, and very few members are actually doing the work of keeping it up. So I decided that wasn't a satisfactory, an all-stone solution was not a satisfactory solution. So then I looked at what happens when we get panels, and we assume that the panels work, but they're interconnected with mortar joints that can only take compression. Is that a structure? Is that a strategy that might work? And a crude model said, yeah, it sort of behaves itself. So then I swapped out some of the panels for some more realistic ones, using finite element models for the pieces. And that's what you get under service wind load. So in this case, this is red is tension, and green is compression, and this is in the worst possible point on the tower. And you can see, you've got an awful lot of tension, pretty hard to take that through unreinforced stonework. But if we add to that a pre-stressed field, so we put some bars through this stone and post-tension it across the panel, both vertically down the diagonals and horizontally at the top and the bottom of each panel, and then apply the wind load, we now get very little tension. We get small amounts around the tips of the windows, probably not a problem, probably something we can live with. But when we put the limit state wind load on again, I've got a lot of tension. But I don't know whether that's a problem or not. Is that more tension I can handle or not? What actually is the consequence of that tension? And so I just did something very, very crude, which is to remove the tension elements out of the finite element model. Do I get a spread of tension, or does it relieve itself? And what we found is that, so you can see where those two blue circles are, is that a compression strut still exists, now at a slight angle to the actual stone strut itself, and makes the whole thing work. In other words, we haven't got a net tension on the section. We've got a net compression. And so it behaves itself. So we decided that was, this idea of post-tension panels is a reasonable strategy. And the next thing is, was it a reasonable strategy for construction? Up till then, the idea was that they would make concrete panels and then clad it with stone front and back. And those are the ones that were getting too heavy, because you had the concrete thickness and the stone thickness and the stone thickness. But they were also taking a week to make the doubly curved formwork, to put the reinforcement in exactly the right place in a finished piece of concrete, to pour concrete in a confined surface, and then to add the stonework. And what we found is we can cut stone blocks now with computer-controlled saws. And actually we could make this panel in a day. No formwork required. Cut the stone accurately, string it together with the rods you see at the bottom here, and hydraulically tension them. And that was the team of the prototype. And the gentleman second from the left is the builder. And he's overjoyed that he can do this in a day rather than a week. Because what we've been set as our challenge, by the way, is to finish the church in 10 years. Okay, they've taken 130 years to build 60% of it. We've got 10 years to build the remaining 40%. Okay? So the whole strategy is to panelize it, bring it to site, assemble the panels, rather than stone by stone or concrete, placing concrete in situ. But stone's a natural material, and we modeled it in a computer. How do we trust the correlation of one to the other? Well, the lucky thing is, having made a prototype, you can test it physically. So we put shear was our major problem, so what we're doing here is shearing it inside a frame, and it behaved almost exactly as we predicted it would, you know, in its post-tension fashion. So we've gone on now to the more real panels. So on the right here, well, left and right is assembling 2 stone panels for the Jesus Tower, and we've got a 1 millimeter tolerance on the assembly part, and they're managing to get there because the stones are all computer cut, but also because you only have to have the accuracy on the bits that interface. The stones in the middle, they can be sort of where they are, provided we get the connections right, and they did. The first attempt anyway, it went together. Reality is still to come, of course, but everybody's now got some confidence that we can do this. And for me to be involved with helping finish what I think is probably the world's most beautiful building, you know, it just makes me so happy that I chose to be a structural engineer, and so pleased, you know, with what I've been able to do. So with that, thank you very much.
Super, thank you very much. Very interesting. Now, any questions from participants?
Mine is not a question, it's more of a statement. It's titled Computers. I think it could be equally titled The Psychology of Structural Engineering and Structural Design. And I think if that presentation could be canned and fed into second level education, we have an awful lot more people coming along. It was an absolutely brilliant presentation.
Thank you.
Anyone else for a question? I might get something in your heard.
Tristram, you're talking about self-checking of calculations and stuff like that. When you're talking about models like this, which are so complex and you're making so many of them on an ongoing basis, how do you see the checking, or how do you get over that checking aspect to give the senior person the level of confidence that they look for?
Okay, so you know, to me, the checking in the computer world occurs mainly by building many models from scratch of totally different complexities. So if my simple stick model and my complex finite element model are agreeing with each other, you know, approximately, then that's a good fundamental check. You should also build the models with different software, ideally. And the Chinese actually stipulate this. For complex buildings, you have to produce 2 sets of computer analysis using 2 completely different pieces of software. So the checking becomes, to me, you know, you can still do all the checking in a machine, provided you use the machine in totally different ways to check itself, if you see what I mean. It doesn't mean you have to, ideally, you know, I do a lot. I actually check by hand as well. Do the reactions equal the loads? You know? There's some basic stuff. And you know, there's a bridge, Helix Bridge actually in Singapore. We were starting construction when I suddenly got a call from the Singapore office saying it doesn't work anymore. And I said, well, hang on, what do you mean it doesn't work anymore? I said, well, we just looked at the analysis and it's all overstressed. And they couldn't work out what the problem was, but they sent us a model, and I was in Sydney at the time. We'd done the scheme design in Sydney and the detailed design had been done in Singapore. And what had happened is somebody turned on gravity in more than one load case. Such a simple thing, but nobody had checked the reactions against, you know, a simple hand calc as to what they expect the loads to be. So there's, you know, it's just an attitude again, I think, of always cross-interrogating. Does this answer look as though, you know, the way it should? But we can't expect a graduate just out of university to be able to do that because they don't know what should is. It's up to us to join in that process and say, does it, you know, is it behaving the way we'd expect it to do? They can do the hand calcs of reactions and loads, but they can't use that, you know, the instinctive thing that we all have, you know, from decades of practice to know whether something looks right. So in answer, sorry, long answer, check. I think the machine can be checked fundamentally using the machine, but by looking at it from very different directions.
Tristram, I heard you first speak in Limerick at a workshop we had done back many years. And then I heard you speak again in Hong Kong about 6 or 7 years after that. And again, here you are, another 7 years later speaking again. And I have to say, every time you do, it inspires me, and I'm sure everyone in this room as well. And the great thing about it is, given the 7-year gap, you've always got pretty good jobs. But I guess my question really is to do with the phase beyond the design medium and the work the contractors do.
Yeah.
My question really is, what are they doing in terms of progressing their design? And are they doing virtual models? Are they doing virtual builds? Or do you have any insight into what the team, the contractor teams are doing?
And just as if you looked at the whole structural engineering design profession, you'd find a very mixed set of answers to that question about what are we doing. If you look at the contracting world, I think it's even more mixed. Right? So at one end, you know, I went out to San Francisco 2 years ago for a thing called the Digital Fabrication Network, where we looked at all the people who are making things directly with digital information. All the people in the San Francisco Bay Area, from molds for facade elements, you know, to directly fabricating pieces of metal using additive manufacturing, etc., etc. So that's sort of one extreme. That's not common. I don't think it will ever be common. But what you are seeing, or what I'm seeing, is some main contractors are really taking on BIM as a logistics program and planning tool to a very great degree. So the Leadenhall building in London, Laing O'Rourke, every single shipment of steel that came there, tight city site, had RFID tags on all the pieces. So when it came in the gate, they could check, is this what we're expecting? Are we ready for this? Can it be put straight into place? If not, send the truck back, let the next one in. Yeah? And then similarly, that RFID tag is still on the piece of steel when it's in place. Has it been put in the right place? All this sort of stuff. They're also pre-assembling subcomponents. So in this case, they were building the core at the back using 40-ton lifts of sub-assemblies. Not pieces of steel now, but sub-assembled steel. Their ambition was to get all the pipework into the vertical risers before putting it into place, from a health and safety perspective, actually, to make sure there were no open horizontal holes. If the pipe was already going through the hole, nobody's going to fall in it. But it also involved pre-assembly of components. So some people are doing this to an extraordinary extent. The sad bit about Leadenhall is they had to build their BIM model from scratch, because we didn't have a contractual route to pass the design model through to the contractor, because nobody thought about it when we started the job in 2006. So in the future, and we're doing it more with steelwork, so Tekla models are now being readily, you know, built by the consulting engineer in a way that the steel industry can use it. They still change it, they alter it, they add their details for the connections and so on, but they start with a chassis that's usable. So I think it takes time, Declan, for the bits of the supply chain to understand the benefit they can get from the other bits, and therefore to change their own working practices to integrate into that. So I see, you know, again, mechanical systems, I see a lot of ductwork being, you know, because the contract says I have to produce a Revit model, people make it after they've made the ductwork, you know, and that's sort of a little bit foolish. But we're getting there, I think, but very patchy.